Hi, in this video I'd like to introduce the method of reducing homogeneous equation in the differential form, and please have a firm understanding about the way we understand the differential equation in the differential form, which the video is available in my website. So let's look at the example. So here's the definition. It's a two-variable function such that if you replace the input with the same scalar factor, then the effect on the values of the function is none. It's actually the same. The main example of this type of function is going to be in the polynomial form. So with the example, it's easier to understand, but it is also important to describe that property of that special polynomial in this general form so that we can establish some statement with using just this property. Slightly general version will be homogeneous if functions of degree n. So if you replace the two inputs by multiply by the same scalar factor t and t, the effect is then not exactly the same, but it's multiplied by nth power of t here. So those are the two definitions, homogeneous function and homogeneous functions of degree n. So you can look at this homogeneous function of degree 0. So here's an example of some degree, not degree 0. It's a polynomial x times y squared and negative x squared times y. Here's y cubed. It is x cubed here. So you can see that this has a degree 3 and that has a degree 3. This seems like just a degree 1 for y part, but there's a degree 2 for x part. Together, it turns out, effect of degree 3. As we replace by the scalar multiplication, you will see where the degree 3 pops up. So here's what happened if you replace t with tx and y, x with tx and y with ty, then all these things replaced by tx and ty. So there's a t, and there are 2 copies of t shows up. So there's a 3 copies of t shows up for the first term, and 2 copies of t shows up here, and 1 copy altogether. 3 copies of t shows up again here. And this is only have t, y in it, so raise the third power of t, and x part also has t in it there, so third power of t. So you can see as you collect the powers of t for each term, they all have this t to the third and t to the third, and that's the degree of each of the term. They're all same for each of the term, so it's so-called homogeneous. So you can factor out that t cubed. I'm sloppy not writing down the rest of the part, but if you look at each of the term without t part in it, you can easily see that's exactly the copy of fxy. So we prove that this polynomial has that property of degree 3, therefore, because we have this third power of t pops out. So this is the main type of the example, and example that is not polynomial of a degree something is very difficult to imagine, but they do exist. But in this course, main example is given by this type of polynomial. So here's an example of degree 0. Okay, so if you replace it with a t and tx and ty, that it disappears the same as the original function value. So I copied these top part here, so you know the numerator has a degree 3, homogeneous degree 3, and denominator, I'm sure you can now easily see that also has degree 3 down there. So as you replace, the degree 3 t cubed pops out here, and the denominator picks up t cubed, and they cancel. The result is that t to the 0, this function value doesn't change. That's the trick. So I wrote it down here. If you replace those x and y with the tx and ty, and we already did this part, so I just wrote down this much, and then you can easily see t cubed and t cubed here. They factored out, and these two cancel. If you look at the rest of the part, that's exactly what we have it over there. So if you replace it with the tx and ty, the function value does not change. So their main example always rises by the quotient of 2 homogeneous polynomial with the same degree. So we were looking at the differential equation, and then we spent quite some time about learning just what those homogeneous equations are. The whole purpose of looking at that very special example, if you randomly write down polynomial, there's a rare chance that it's going to be homogeneous polynomial of degree something. The whole point is that the special example of non-separable differential equation turned in through the algebraic trick to a separable equation. So here's why. If you're looking at two variable functions, which these appeared as a coefficient in the differential equation in differential form, if they're two variable, it's not good for a separable equation, right? But there's a way to turn that into one variable function here. So if there's a two variable function, it's actually a two variable function, but it really behaves like a one variable function here. That's what I'm asserting. This, if you have these homogeneous functions, you can turn that into a one variable function where the variable is just really y over x. So this is a theoretical statement. In practice, it's a lot easier to see, but it's phrased this way to make a connection to our separable equation, which required one variable in front of dx and dy in that differentials. So I put it up here and looking at this example. So this is a homogeneous function, degree 0, like we saw that before. I think I changed that to positive, but it could be negative, it doesn't matter. So how are we going to turn this one into a function of y over x? So it's such that everything here is going to be written in terms of y over x. That's what it says. So there's no y over x here. So if I want to pull out y over x, then you're going to divide everything y over x. For example, if you want to pull out y over x here, you're going to factor out x cubed, for example, then this y cubed divided by x cubed will show up. So that's the main technique. So in the numerator, if you factor out x cubed everywhere, then it already had one copy. So the two copies and it goes to the denominator. We had two copies, so the one copy goes to the denominator. So you have to really do the factorization. It turns out something's really nice if you have y squared, there's x squared there, if there's y to the first, then x to the first there, y to the third, x cubed, and a constant. So you can see everything here is in terms of y over x whole quantity squared, y over x here, y over x whole quantity cubed plus 1. So that's really, everything is written in terms of this y over x. That's what they mean by this one. Let's see what happened. In the denominator, I'm sure we'll pull out x cubed and similar thing happen because it's a homogeneous degree is the same. So if you pull out x cubed here, and we have this y cubed divided by x plus 1 here. So this is just y over x whole quantity cubed. So that whole thing, x cubed and x cubed cancel, and if you label this y over x with a v, then this is going to be one variable function. Like here in this example, that it's going to be v squared, the other one is negative v, everything is in v, so this whole quantity is really one variable. We can write down as a one dependent variable in this case is y over x is v, which is what I wrote here. So that function they're talking about is really this one variable rational function, v squared and so on. So that y part is exactly what is picking it up. So here, if you focus on this statement, the qualitative part of the statement, not how you go from here to there, the whole point is that now we have something in front of dx and dy was two variable. If that has this very special property, then we can turn that into one variable. That is good for a separable equation. But there's other parts that you have to worry about, but something nice still happens. So here it's example we're going to try, and then I'm going to give you what's sort of a general formulation. So here is an example, y prime equals y plus x divided by x. So this, let's change it into a differential form and see if that's a separable equation. Well, I'm just noticing here before I do that, right hand side is a homogeneous equation. So you have a degree 1 up here and degree 1 down there. So it's going to be degree 0. So t will cancel. It's a homogeneous equation. So there's a way to turn this one into one variable function. Again, before we enter this differential form, I'm emphasizing here, although this part here is y as a function of x, when we enter differential form, we're really looking at y as a function of t and x as a function of t, and entering this Cartesian equation parameterized by t. In that way, the differential form with dy dx makes sense. So by looking at this dy dx, and x is multiplied to dy, so that's why you have it here, and dx is multiplied to that part. So if you look at it this way. So that is equivalent to this differential form. So in front of dy is a one variable x, whole thing. In front of dx, unfortunately, it's not. If there's one variable, you can just swap it or leave it there, and that's typical separable equation. So the problem is here, it is not. So idea is that if you pull this x out, just like we did in an earlier example, that it's going to turn into y over x. It's going to be a one variable function, and something nice happens. If this is degree 1, that's going to be also a one variable function. To understand why this magic happened here, it's understood better when you do this in general, but let's go through this example first. So you see I'm pulling out x, it's y over x now, plus 1, so that's going to be one variable, v plus 1. And we're just going to leave it x there, and you can see this x and x cancel. Right? This cancellation always happens. Why is this canceling? Is this just like that x cubed canceling in the earlier examples? It's x to the first is the degree of the homogeneous equation of this one and homogeneous equation of that one. They cancel out. So that's going to be always happening. So once you cancel this out, assuming, of course, when we enter this one, we assume x is not equal to 0. So this way of solving equation excludes what happened at x equals 0. Of course, here we kind of assume that we're not interested in x equals 0. So the next process is turning this one really into a variable in terms of v. So that's going to be easy, v plus 1. But we're keeping this x as the main variable and decided to change y in terms of x and v. So that's what we're going to do, y equal vx. This is wrong. This is supposed to be t in there. So we're looking at the v as a function of t here. Okay, got it now. So v is as we're looking at the function of t here. That's how what this context is about. Now here's x is cancelled, and let's rewrite this y with this vx in there. So that's going to be now v plus 1, and this y is replaced by vx. Let me explain what this is. This is a derivative of v times x, where v and x are a function of t differentiating with respect to t. That's what that is. So you're going to apply the product rule, of course, to that. Let's shook a little bit. It's a v plus 1. The derivative of v is there, and derivative of x is there, and the rest of the part is just functions of t. So that's what's going to happen to this part, simply the product rule. So we're going to collect this dx, and v plus 1 and negative b cancels, and dv is the only term. So there's negative x. So here it is, 1 times v cancelled and 1 times dx minus x times dv. So this is one variable, and it's one variable easily, so you can easily separate that by dividing both sides by x in here. If there were b and v in there, you will divide that too, so you will put it over there. So it looks like this, 1 over x and negative dv, and is completely separated, and from here is usual separable equation. So I'll show you, and you can do this yourself. Pause the video and you can do that yourself, and then check the answer with me. Right, here's the way I did it, and make sure when you go through the antiderivative 1 over x, you pick up ln x there. So your solution includes this ln x in there. You know ln x is not defined at x equals 0, so it gives you a completely different solution set to the right of x equals 0 and to the left of x equals 0, and it's undefined around x equals 0. But you can certainly look at the behavior around that x equals 0, and that's sometimes the main part of the interest.